Thank you. Okay, let's go ahead. You follow that screen for the time being until someone's in. Please, we have wasted a lot of time. I'm really sorry. So, moment distribution method. I'm going to just explain how it works, okay? If we take an example of a beam, so we have a two-span beam, okay, with support in between the, so we have A, B, C, okay? A and C are fixed, right? And B is a simple support. Is that clear? On AB we have a concentrated load in the middle, and on BC we have got a uniformly distributed load. So the concentrated load W is 10 kilonewtons, and the UDS, the uniformly distributed load, we assume is 2 kilonewtons per meter. Right? Given this is 5 meters, this is 5 meters, and BC is 12 meters. All of them? Oh, thank you. Okay, lovely. Thank you very much. Okay, so as I said earlier in the introduction, if you want to solve this using momentary equation, using the equation of equilibrium, you simply will not be able. Okay, because how many unknown reactions do we have here? Can you count them? How many at A? 3. Yeah, vertical reaction. You have a vertical reaction, you have a horizontal reaction, and you have moments, okay? Then you have 3 at C, so that's 6. And then you have 2 here, so that's 8. Yeah? So there are 8 reactions, and there are only 3 equations of equilibrium. So we have got 5 too many. Is that okay? Yeah? So we have 5. We have a total of 8 reactions, okay, and only 3 equations of equilibrium. Okay, and therefore, the structure here is statically indeterminate. It's statically determined. Okay? Okay. So in this case here, the use of the moment distribution will be moment distribution method will be very appropriate. I'm going to explain the steps on using the moment distribution method. Okay? So we are going to use the moment distribution method to solve this problem here, okay? Step number 1. Instead of going into the theory, deep into the theory, I don't want to do that. First of all, we haven't got the time. And secondly, you may not have the background to it. So it's a lot easier if I explain it in terms of step by step. So step 1, 2, 3, and then it becomes very systematic, okay? Step number 1, you split up the continuous beam ABC, into fixed-ended into fixed ends beam elements. So you split up the continuous beam ABC into fixed ends beam elements. What do we mean? We mean this is the beam here, ABC, and we are going to split it into two here, like this. So now we have AB and BC. When you split up a continuous beam, remember this, when you split up a continuous beam, right, always the intermediate support here becomes fixed. Okay? So always the intermediate support becomes fixed. Is that clear? Okay? Now, so we have got this load here and we have got the load there, so we have 10 and 2 kilonewtons per meter. Okay? This is 10 meters. Okay? I mean, these two here are the same, and we have 12 meters for BC. Is the first step clear? Yeah, clear. Step number 2. Step number 2, using the table, determine the fixed and moments for each B. You might have copies. No?
Yeah, I've got that one. I did the both. I've done that one.
I know.
You've got that.
Okay, so I missed it here.
Only did that because he started doing it.
Right, okay, so step number 2, let me explain this please. So step number 2 here, using the table, this table here, all right, using the table, determine the fixed moments for each B. Now, if you look at, if we start with AB, okay, this is AB. Here we have W 10 kilonewtons, and we have a span of L 10 meters, okay, and the load is in the middle, okay, and that's AB. So which case is this in the table? Do you agree it's the first one? Yeah. So the first case is applies here. So we have got a fixed moment there at A. We call this fixed and moment AB. Okay, and the moment at B is the fixed and moment BA. Okay, and you can see the sign convention here. The moment at A is anti-clockwise, and therefore it's negative, and the moment at B is clockwise, and the values are obtained from the table. Do you understand the direction of the moments or not? Does everyone understand why the moments are in that direction? If not, I can explain it. No. Okay. This is the beam. Listen here. Yeah. This is your beam, and it's fixed, right? So it's rigidly fixed here. Imagine you apply load here. Okay. Imagine you apply the load in the middle, and your beam is fixed like this. When you apply the load, the beam is going to deform, isn't it? So, in order to prevent this deformation of the beam from in order to prevent the beam from deforming, you need something that pulls it back. Do you agree? So you've got a moment here going in this direction. Do you agree? And on this side here, okay, as the beam goes down to deform, you need a moment, you need something to pull it again to prevent it. In other words, you need a moment in this direction. Is that clear? So you've got a moment in this direction and a moment in this direction, which is what we have there. Yes? Agreed? Yeah? Does it make sense or not? Yeah? Okay. So, by convention, this is a pure convention. If it's anti-clockwise, it's a negative sign, and if it's clockwise, it's positive. Okay, and therefore we have got these values here, right? So we have at A we have a moment minus Wn over 8, and at B we have a moment Wn over 8. Okay, so we have So we have FEMAB. This is the bending moment at A, is minus Wn over 8, which is minus W is 10, L is 10 over 8. Is it 12.5? Minus. Yeah, kilonewtons meters. And the moment at B will be the same plus 12.5 kilonewton meters. Plus Wn over 8. Right? So we use this equation. Is that clear? Yeah. Now we do the same for BC. Remember BC, we have this time we have BC like this, fixed, and we have W is 2 kilonewtons per meter. Okay, and we have BC. So we have a fixed end moment at A at B, BC, and CB. You know, the first subscript is always refers to the joint itself. Can you see that? So here we have FEMAB, it refers to joint A. FEMBA refers to joint B, etc. Is that clear? So now we use the equation. So we have FEM. Which one we are using? Which number? Third, you agree? Yeah? So we're using this one here, number 3. Okay? And the moments are minus Ws squared over 12 at A and Ws squared over 12 at this end. Is that clear? So we use that. So we have minus Ws squared over 12, which is minus W is 2 times L is 12 in this case, 12 squared, divided by 12, which gives minus 24 kilonewton meters. And the fixed moment at B, at C, CB, is plus 24. Okay, any questions? Yeah, so that's the second step. First step, split up. Second step, determine the moments from the table. Now we get to the next step, step 3. So we started with a continuous beam, and then we split it up into 2. Yes, A, B, and B, C. Now we want to put it back. So split it up. Now we want to put it back. Let's see what's going to happen here. So this is the beam here, A, B, and this is B, C. Right? See that? So at A, we have a moment of 12.5 anti-clockwise. At B here, we have got a moment of clockwise 12.5. At B here, for BC, this is AB, we have minus 24, and finally at C here, we have 24. Okay, now, if you want to put it back now, okay, if you want to put it back now to where it was, what's the problem we have? Because now we have a problem here. Sorry? Yes, isn't it? Do you agree? Because look, this is your beam, fixed at 2 ends, and there is an intermediate support, yeah, at B. Okay? So you have got B, A, C, and you've got intermediate support at B. The beam is continuous. It's one beam continuing from A to C, yeah, resting on a support at B. So the moment at B, left and right, is the same. See that? The moment at B should be the same because it's one beam continuous from A to C, resting on a support at B. So at B, you should have the moments left of B and right of B the same. But it's not. Okay? It's not balanced. It's not in equilibrium. Right? So here, we have an out of balance. An out of balance. How much is the out of balance? Sorry? That's positive, that's negative, yes, according to convention. So what's it? So we have minus 11.5. Do you agree? How much do I need to add to B to make it balanced? How much do I need to add to B to make it balanced? 11.5. Do you agree? Because we have minus 11.5. If I add plus 11.5, that makes it balanced. Agree? So I put between brackets here, balancing moment equals 11.5. So you have the out of balance and you have what you need to make it balanced. Okay? Is that right? Yeah. Now, the question is, how do we balance? How do we balance it? That's the question.
by increasing the weight of AB?
Yeah, the question is how do we balance it? How do we, okay, let's say I've got two people next to me. Yeah, one on the left, one on the right, and I'm here, and I've got really heavy weight. Okay, I've got two things to, something heavy, and I want to distribute it. Do I give them the same weight, or I have to give them in proportion to their strength? Exactly. Yep. So here you've got AB. AB is 10 meters long. BC is 12 meters long. So obviously you've got two different beams. They may have different sections as well. You don't know, right? They may have different sections. They have different lengths. So obviously, if I want to distribute that moment here of 11.5, I need to give each beam in proportion to what we call its relative stiffness. Okay? This is what defines the ability of a beam to take moments. It's the stiffness. Okay? Now, and we define what we call, and this is the next step actually. Okay? We define the concept of distribution factors okay, that allows balancing of the moments. Of the outer balance of the moment. Okay, I'll just put it. Okay. And intermediate joints, intermediate supports. Okay, so we are going to define what we call distribution factors, DFs, that allow us to actually balance the outer balance moments at the intermediate supports. Okay. And we defined the distribution factors at given joint. That's the definition here. Okay. So a distribution factor for member Ij in general, I'm giving you a general definition, and then I'm going to use it for A, B, and DC. Okay. So distribution factor for stiffness. Sorry, distribution factor for member Ij is equal to stiffness of stiffness of the element of the beam, at stiffness at joint I, divided by stiffness of all members meeting at joint . Okay? Is that okay? An I. Always I is the joint, the first subscript refers to the joint itself. Okay? Okay. Look, I make it clear. So stiffness of member Ij, divide that by stiffness of all members meeting at the time. How is that? That's good. Yeah. So it's the stiffness of member Ij divided by stiffness of all members meeting at I.
What's number IJ there?
IJ is just a member IJ, okay? All right, I'm going to, now we can use it for AB and BC. So for AB will be IJ will be AB. For BC, IJ will be BC. Okay, so it's so this is IJ. Okay, so you have a member and you've got joint IJ. I mean, you could, you know, your joint I here could be connected to more than one member. So what you do, you take the stiffness for IJ will be the stiffness of member IJ here divided by stiffness of all members connected to joint I. So you could have more than one member connected to joint I. Let's use it for this here, for this beam. Okay, let's say that this beam has got a flexion rigidity EI, and this beam also has flexion rigidity EI. Do you understand what I mean by E times I? What is E? E, what is E? You agree? Do you know Young's modulus? Yeah, I, second moment of area by mutual axis. Yeah. So in the case if you have got a, if the beam has got a rectangular section, I will be what? Do you know what is I for rectangular section? B to Q over 12. Agreed? Yeah. And E will be your Young modulus. So if you have got a beam made of steel, for example, E will be 200 kilonewtons per millimeter square. All right. And I will be your, as I said, your I. Your second moment of area. Okay, so let's use that for this beam here. So I'm going to put it there. So we have one. Imagine that this A here, that we have got a wall. So it's connected to a wall, and then at C it's also connected to a wall. So you have got a beam running from wall to wall here. Is that clear? Yeah. And in the middle, you can imagine this is being a column, for example. So you could have a beam running from wall to wall and then resting on a column there. Is that clear? So we have three joints. So we have joint A, we have joint B, and we have joint C. Okay, now look at A. Look at A here. How many members are connected to joint A? One member, isn't it? Yes? And then on this side there is a wall. So we have DF A, B. Okay? Then at B, can you see here at B we have two members, isn't it? We have BA and BC. So we have DF BA and DF BC. Okay, this is for joint B. And finally, how many at C? Do you agree CD? Yeah, we have CD. Let's use the definition. Let's use the definition. By the way, way, we define the stiffness of a member by, it will be the EI divided by the length, by the span of the beam. Okay? Here it will be the EI times divided by the length of the beam. All right? For AB, so let's use distribution factor for AB. AB. So A is IB. Okay? So stiffness of member AB. What is the stiffness of member AB? What is the stiffness of member AB? EI over 10. You agree? So we have EI over 10. Right? Divided by stiffness of all members meeting at A. Okay? All members meeting at A. At A we have EI over 10. Yep. And we also have the wall. We can't just ignore it. But we assume that the wall is infinitely rigid. Because remember, this is fixed here. Yeah, this is fixed. Right? So we assume that the wall has got an infinite rigidity. Very large. We don't have the value, not given. So it's very large here. So this is the wall, if you want. Now, if you divide something by something very large, what do you get? If you divide something divided by something really large, if you divide by infinity, what do you get? Do you agree? 0. Yeah? If you divide by a very, very large number, you get 0. Okay? So here we have 0. So whenever you have got a fixed support, remember this in the future, you don't have to do that all the time. Whenever you've got a rigid support like this, the distribution factor is 0 at that joint, because it's rigid. Yeah? Because it's rigid. Now let's do it for BA. We have stiffness of BA. What is stiffness of BA? Look at the figure. Sorry. What is the stiffness of BA? EI over, sorry, BA. 10 divided by stiffness of all members meeting at B, first subscript. So we have EI over 10 plus what? EI over 12. Thank you. So the EI can simplify, so we have 1 over 10 over 1 over 10 plus 1 over 12. If you've got a calculator, you can work this out for me, please. You can check it, please. I've got 0.55, not 0.55. Is that correct? Yeah. If you want to leave it as a fraction, make it common denominator and so on, I think you find 6 over 11. Yeah, 6 over 11 or 0.55. Isn't it? Yeah, that's it. Okay? Agreed? Okay? Now, for BC, we have stiffness of BC. What is stiffness of BC? EI over 12. Divide by stiffness of all members connected at B. First subscript here. So we have EI over 10 plus EI over 12. Again, the EI will simplify, so we have 1 over 12, 1 over 10, and 1 over 12. Again, please do check it. I've got 0.45 or 5 over 11. What do you notice here? 8.1. It's actually actually by the definition itself, because if you add the distribution factors at a given joint, right, you get the numerator equal to the denominator, and therefore you get 1 all the time. Okay. So as a check, the distribution factor at the sum of the distribution factors at a given joint is always equal to 1 at an intermediate joint. Okay. So here, check the sum is equal to 1. Okay. So as a check, you can see that the sum of the yes.
Do they not need a unit of EI? Because essentially you've taken it out. What does the EI get?
Sorry?
So does the EI, does that not become like 0.55 EI?
Because you've got EI at the top,
yeah,
and you've got EI, so it cancels all the time. It's always like this. The EI will always cancel. In the future, you don't have to carry with you the EI all the time. You can always do 1 over 10 and 1 over 12. Because this is here, this is here like having 1 here, okay? So you've got 1 there, can you see that? And you've got 1 here. Yes? So you have 1 over 10 and 1 over 12. Is that clear? Yeah? Because the EI will just cancel all the time, always. Lastly, for joint CB, we have stiffness of CB, which is EI over 12, okay, divided by, we have EI over 12, and then you have the wall, which is again infinity, so that gives again 0, roughly equal to 0. Okay? Any questions?
How do you find out now? Are you going to add additional weight? You know, do the weight.
Oh, that's the next step.
Oh, that's the next one.
Yes, that's the next step.
I just falls into it, doesn't
Yeah, I just want to open a bracket here. Write it on a separate sheet of paper. Yeah, it's nothing to do with the example. I just want to explain something. Let's say, for example, okay, let's say I've got this pin here, 3 spat, for example, okay? Okay, this pin has got a rigidity of EI, this one has got 2 EI, and this one has got, let's say, 1.5 EI, for example. Yeah, and let's say this is 3 meters. Let's say this is 4 meters, okay? And let's say, for the sake of it, let's say this is 2 meters. All right? And I have A, B, C, D. So we have joint A, joint B, joint C, joint D, right? So for joint A, we said earlier it will be, what did we say? If it's a fixed joint at the end?
0.
0. So, okay. So now we have DF BA and DF BC. So we have two members. So BA, for BA, look here, for BA, I have, this is like having 1 here, isn't it? Yes? So for BA, we have 1 over 3. So I can ignore the AI, 1 over 3 divided by 1 over 3 and 2 over 4. So 1 over 3 and 2 over 4. Do you see that? Is that clear? Yes? Because at joint B we have 2 members. We have member BA and member BC. So we have 1 over 3 and 2 over 4. Yeah? So if you can work it out for me, please, quickly. is stiffness of BC, which is 2/4, divided by stiffness of all members connected at B here, joint B. Okay, so we have 1/3 and 2/4. So if you can calculate this for me, please. It should be 0.6. You check it. Can you see that the sum is 1? Let's do CV. I'm going to ask you to do this one for me, please. Can you do on your own, please? Distribution factors for CV and CV. And then give me the answers. And give me a shout if you are struggling or if you don't understand. Probably. It would be a pure coincidence.
Yes.
Are they going to be the same one? I'm going to be a little bit. Let's make this 3. So they are not the same. All right? Let's make that 3. Let's make CB 3 meters. Work it out. So it would be 2/4, isn't it? Yes? And at the bottom, what do we have? Because remember, we are at joint C. We are at joint C. That's joint C. The first section is joint C. So we have 2/4 divided by 2/4 plus 1.5/3. Correct? Yeah. And at the bottom, we have 1.5/3 divided by 2/4 and 1.5/3. So what answer do you get? 0.5. Here. It will be, yes, actually. So the sum is 1 again. And finally, for joint D, we have DF, one member, DC, and it's 0. Is that clear? So whenever you have got any members like this, any beams, as long as you know the span and you know the rigidities here, the flexion rigidities, you should be able to determine the fixed end moments, the distribution factors at each of the joints using the equation.
On our example, we kind of such as EI for our example.
Yeah. In our example, it's it's the same EI that we have for both of them. Yeah. If I change the values here, everything else will change, right? Have we finished with this, please?
Yeah.
Yeah, everyone? Thank you. So this is just a, extra to explain. Let's go back to our problem. So now we've got the distribution factors, right? We have determined the fixed end moments. We have determined the distribution factors. Now you can ask me, what does it have to do with this here? Because remember, we need to balance this. Yeah. So that's the next step. Step number 5 we need to balance.
Part of the first example, isn't it?
Sorry?
It's part of the first example.
Yeah. Now we continue the first example, okay? Now what we are going to do what we call the process of balancing and carrying over. So now we balance and carry over. And let me explain this, okay? So if this is our B, and we've got support there, okay? And we've got moments, if this is A, B, C, okay? We've got moments at B, sorry, here, left and right of B. So we've got moments there, at left and right of B. And these are the moments we are trying to balance here, okay, at B. We are going to balance the moments using this distribution factors concept. But also there is also something else we need to do is, do you agree that the moment at B will affect the moment at A or not? Do you think that anything happening at B will affect A as well? You agree? Yeah? So, we can prove it. Again, I'm not going to prove it because it will take me probably an hour to do that. When you balance here, the moment at B, the moment A will take half of the moment from B. Half. Okay? And similarly from there to there, this NC will attract half of the moment from this moment here. That will be the effect of B on A and on D. So always, when you have an intermediate joint, the adjacent joints, the immediate adjacent joints will attract half of that moment. And this is what we call carryover. So you carry over half. You carry over half. So you carry over half from B to A, and you carry over half from B to C. I'm going to explain this in a table, okay? So moment distribution table. And I'm going to explain it, okay? Moment. Can I ask you to leave? You need some space here. You need probably about half a page, at least. Short table. That should be it. Okay, so we have a table here. 1, 2, 3, 4 rows. In the first row, we put the joints. In the second row, we put the members. On the third row, we put the distribution factors. And the final row, we put the fixed end moments that we have calculated previously. How many joints we have? 3 joints. We have joint A, joint B, and joint C. How many members are connected to A? 1. Do you agree? It's AB? Good. How many members are connected to B? BA and BC. Thank you. And finally, we have 1 member connected at C, and that's member CB. Okay, distribution factors. We know the distribution factor at A. For AB, we have 0. For BA, we have 0.55. For BC, we have 0.45. And finally, for CB, we have 0. Distribution fixed moments, we have calculated earlier. Fixed moment for AB, we have minus 12.5. Then we have plus 12.5 for BA. For BC, you can see here we've got minus 24 and plus 24. Minus 24 and plus 24. Okay, now, here we have the out of balance that I've mentioned earlier. In other words, the balancing moment will be plus 11.5, okay? The balancing moment will be 11.5. This is how much we need to add to the joint to make it in equilibrium. So we are going to take the balancing moment because we are going to balance. That's the first step. The first step is to balance. So when I balance, I take the balancing moment and I multiply it by the corresponding distribution factor. So remember we are balancing joint B. That's the intermediate joint. Okay, these are end joints. We are balancing the intermediate joint B. So you take the balancing moment, you multiply it by the distribution factors. 11.5 times 0.55. So you do 11.5 times 11.55. I've got 6.33. Is that correct? Plus. So you do 11.5 times 0.55. Yeah, 633 to 2 decimal places. And we have got 11.5 times 0.45. I've got 517. Yeah, okay. What do you notice when you add these two together? Exactly, you get 11.5. Yeah, you get 11.5. Now, what did we say earlier? We said we carry over half from B to A. Yes? We carry over from B to A. So from joint B to joint A, from joint B to joint A, I carry over half. So what is half 633? 3.17?
Yeah, 1 second.
Okay? So this is carry over. Okay? And we carry over from B, can you see here, from B to C. We carry over from B to C, half. So you carry over from B to C, half. So 517 half is 259. Thank you. 25. Yeah. Now what we do, we have balanced, we have carried over. So now I'm going to draw a line here. Can you add this moment for me, please? The fixed end moments with the moments in the table, not the balancing and the negative, but this here. So minus 12.5 plus 3.17, 12.5 plus 63, minus 24 plus 517, and then plus 24 plus 259, and put the answers here. I've got minus 983. Please do check it. 33, sorry. Yeah, and I have 1883. Is that correct?
Yeah.
Yeah, and I have minus 1883 for this column here. That's minus 24 and plus 517.
Yeah.
And finally, I have 26.59. Correct? What do you notice? What do you notice here? Balanced, because remember that was the whole purpose, was actually to get the joint at B balanced. And you can see here that the moment left and right of B are equal and opposite. So now we have got equilibrium here. Okay, in other words, joint B is now balanced. Joint B is now balanced. So we have achieved the objective, right? So the distribution factors, as you can see, by defining the distribution factors, we have managed to get the out of balance moment here balanced, right? And each beam has taken a proportion of that member, which now we have got the joint that be perfectly balanced. I mean, we've done it slowly here, but you can see that when you know the method, it's very systematic, and it doesn't take 10 minutes to actually do the whole lot, okay? Because we've been doing it slowly, explaining and so on. The more examples you do, you find that the method is very, very simple and systematic to use. Because really, all you have to do is determine the distribution factors and the fixed moments. That's it. Once you've done that, you draw your table, it gives you the moments straight away. Is that okay?
Yes.
Yep. Any questions? Any questions about the table or any of the steps? Yes.
So I missed how you got so from the balance.
How did I what, sorry?
So how did you get the figure plus 517? So from that.
This one, half.
So from the balance, the figures there, how you got
This one. 11.5 times 0.55 gives you this, and then 11.5 times 0.45 gives you this.
And the two.
Yeah. So you multiply the balancing moment. You multiply it by the distribution factors, which gives you these two, and then from joint B to joint A, you carry over half. Okay. From B to A, you carry over half, and then from B to C, you carry over half. Okay. Any questions? Yeah. All right. Now I'm going to. So this is what we have at the moment now. Are we okay to, yeah, because we are meeting again at 2 o'clock, isn't it?
Yes. Yes.
Okay, that's fine. Right, okay, please, can I have your attention? So we have, this is the beam here, AB, and this is BC.
and B.
Yeah. We're same example, right?
So is this example of continue to step 6?
If you want, now we're going into step 6 if you want, yes. Can I get attention, please? Can I get attention? Now, at joint A, please, can you see, what do we have at joint A? We have minus 933. What does it mean, minus? Clock or anti-clockwise? Exactly. So we have, at A, we have anti-clockwise 933. Then at B, on BA here at B, I have a 83 clockwise. Okay. Then at B, on BC, I have anti-clockwise 1883. And finally at C, I have clockwise, positive clockwise 2659. Can you see we went from this situation here earlier, do you remember, to this situation? Pass. Okay. And remember we have got a point load here, we have a concentrated load and a median, obviously. Look at this beam here. Look at AB. See AB? AB we have, okay? We have a moment, anti-clockwise moment, yes? So we have an anti-clockwise moment. Can you see that? So where is the tension, at the top or at the bottom? At A. Is the tension at the top or is the tension at the bottom? Do you agree the tension is at the top? Where is the tension here at B? This is the moment. So where is the tension, at the top or at the bottom? At B, on that side? Let's see. Top. It's just happened that in this particular example, the tension is at the top everywhere. But it's not always the case, okay? You may have situations, we look at some examples in the future, where you could have the tension at the top or the bottom. It depends on the loading and the supports, okay? The reason I'm doing this, showing this tension, where the tension is this. When you draw the bending moment diagram, which is what I'm going to do here, so bending moment diagram. Okay, the bending moment diagram. When you draw the bending moment diagram, always plot the values on the side of the member where there is tension. Okay, I repeat, when you draw the bending moment diagram, always plot the values on the side where there is tension. For example, here, the 9.33, we plot it at the top or bottom? Top. Again, here you can see 1883 is at the top. And finally, at C, we have at the top 2659. Now, how do I join these points together? How do we join the points together? We have a concentrated load on AB. If you have a concentrated load, what is the shape of the bending moment diagram? Constant, linear, parabolic, what is it? Constant, constant, linear, parabolic. Sorry? Concentrated load. Linear. Linear. If you have a concentrated load, the bending moment diagram is linear. Okay? So here you have got, so from there, you've got a linear diagram like this. Because you've got a load in the middle there, so this is the shape of the bending moment diagram. Now, for BC, we have a uniformly distributed load, so the shape will be parabolic. Just remember this, please, okay? So when you have concentrated loads, it's linear. When you have a parabolic, when you have a UDL, the shape is parabolic. Right? The only thing left, we need to determine the points of maximum moments. What do we call these points here? Any idea? What do we call these points here? Where these are the points of maximum moment. Okay. What do we call the points where this is where the bending moment is 0, isn't it? These points. Yeah. We call them points of contraflexion.
Over the maximum compression.
What does it mean, point of contraflexion? The point of contraflexion is the point where the curvature of the beam changes from tension to compression. Yeah? So it's where the beam changes from tension to compression. We call it point of contraflexion. Is that okay? Yeah. So you have a change here from going from tension to compression. You've got change there. So therefore, that's a point of contraflexion. Contra means opposite. Okay. So you have opposite flexure from left to right. There is a change. Okay. So it goes from tension to compression or vice versa, and that's why we call it a point of contraflexion. And this here corresponds to M. Bending moment 0. These points here correspond to points of maximum moments. So we need to find these points of maximum moments, and we need to find the position of the points of contraflexion. Is that okay? Yeah. And this is what we need to do this afternoon. So this afternoon at 2 o'clock, I'm going to spend, I hope, half an hour to do this, and then we do something else. Is that okay? Okay. Yeah, it's 10 to, so I think we give you a break, and we're meeting. Is it this room? No, I think we are in this room, isn't it?
It says ECGO2, so I'm guessing it'll be here.
No.
It will be here.
I think so. Yes, I think so, because they should have informed you. I think we are going back to ECGO2, yes. Anyway, at least we are in the same place. So I check it again, and I'll let you know. Okay? Thank you. Yes, sure. Here? Yeah. Because we want to balance. You see, you've got minus again. Ideally, you want this difference to be 16. Yeah, you want this difference to be 16. So you want to add that 11.5 to make it 0. Exactly, that's it. That's how it works.
Do we actually have to?
That's not true.
I'd rather it be longer.
No, what is going on? So we have to tell them. What have you got?
We're going to study.
I wish I knew. Then I
We can sort it, yeah.
could go home early.
Yeah, but that's it.
Should we do that?
Hello, everyone.
Yeah, they've got some of them.
Do you want to have a 15-minute break?
No. Some of them have left. I
Can we do that?
don't want anyone complaining.
Thank you for telling me what happened.
The ones we have in the room, actually. That's the problem. Yeah.
Maybe sorry for tomorrow.
Yeah. I'll change the subject and try to sort it for tomorrow.
Reduce the gap.
Yes.
So tomorrow we've only got one anyway.
Well, there's no point spending 4 hours.
I think it's going to be that way. I think so.
It's like half a week.
You just have to.
Very well. That's so much better.
All right. You too. See you later.